Hi, in this video, we want to take a look at the F distribution. Okay, the F distribution, its primary role in statistics is to check to see if two samples have the same variance. All right, so the idea here is that I'm going to take two different samples. I want to know the populations, are they coming from, is the sample coming from the same variance? Okay, well, what we're going to do, we're going to put them on top of each other, our sample variances. And then we're going to check to see, is that ratio close to 1 in terms of a probability sense? We're going to use the F distribution to evaluate, we're going to use the F distribution to reach a conclusion. Okay, so the point where this comes up the most for most people is in ANOVA. So if you look at an ANOVA table, over far to the right, you'll notice that there'll be an F statistic. Well, once we have that F statistic and we have the degrees of freedom, we get our p-value using the F distribution. So there you go. So whenever you're doing ANOVA, you're actually using the F distribution. You're performing an F test. All right, so to help us better understand that test and the F test itself, let's go ahead and look at the F distribution right now. Okay, so here is the probability density function. All right, so there is a lot to unpack here. All right, the part to always look at the most whenever you're looking at a density function is to look at where the variables are and ignore the rest in the initial part. Okay, so here I see that I've got x to the power of d1 over d2 minus 1. So d1 is the degrees of freedom for the first parameter, and d2 is the degrees of freedom for the second parameter. These will correspond to the ratio of the variances. d1 will correspond to the top, and d2 will correspond to the bottom, the denominator of the fraction. Okay, and so inside here, we see that we have an x, d1 over d2 and 1, and then we have the average of our degrees of freedom over here. So focus on this part first. This is the part you need to understand. This is what we call the kernel. Okay, now the stuff over here, from a statistics point of view, this is just a constant value that is used to make sure that when I integrate all of this junk, I end up getting 1 for the total integral from 0 to infinity. So here we have gamma of d1 plus d2 over 2. We have gamma of d1 over 2. We have gamma of d2 over 2. We have the fraction of the degrees of freedom. And then we have d1 over 2 right here. Okay, now possible values for x has to be greater than 0. In some cases, x can be equal to 0, but that's such a small point, not really worth talking about. The expected value is d2 over d2 minus 2. Now, something to notice about this is that, first and foremost, there's no d1 involved. The expected value has nothing to do with what d1 is. Isn't that kind of weird? Isn't that surprising? We have an entire parameter not involved. Now, another thing to notice is that we've got a fraction and d2 minus 2 on the bottom. Therefore, d2 has to be greater than 2. Okay. Now our variance has a very beautiful formula here for us. d1 plus d2 minus 2. We have d2 squared. We have a 2 here. Down here we got d1, d2 minus 2 squared, and then d2 minus 4. So there's a lot of stuff to unpack. There's a lot of stuff going on. It's not, if you give me particular d1s and d2 values, it's not exactly clear immediately just glancing at what the variance is going to be. Now, to make sure that we don't do something stupid, we have to have d2 greater than 4. Otherwise, we have something that doesn't make sense. Okay, so now let's try to connect the F distribution to the chi-square distribution. We just talked about just the density itself, but now what we want to do, we want to go, hey, this is how we get variance to F distribution. Let's say that U1 and U2 are independent chi-squared random variables with relative d1, d2 degrees of freedom. Then this fraction is going to be F distribution. So U1 over d1, U2 over d2, take the ratio of those two fractions. All right, this fraction here has an F distribution. with D1, D2 degrees of freedom. All right, so what we're going to do, how we're actually going to use this for an F-test, is that we are going to take our sample variance divided by the population variance, and then we're going to take sample variance divided by population variance, take the fraction of those two fractions, and then this is going to be how we're going to address the equality. We're going to address the ratio of the variances. Okay, now that's the ratio of the population variances. Now, typically what will happen when we're doing this, we're trying to see if the two variances are equal to each other. Well, if sigma 1 is equal to sigma 2, then this fraction, these cancel out, and all I'm left with is the fraction of sample variances. Huh. All right, and so this gives us a way to do hypothesis testing. So I have a statistic and I have a distribution, which means I can do hypothesis testing. So here, this gives me the test statistic to work with when I do hypothesis testing. The distribution gives me a method of evaluating what is the p-value. And then once I have the p-value, I can decide, are the two variances equal to each other, or are they different? How do I make, what conclusion do I reach? Now here's some important properties of the F distribution. The F distribution has an inverse property. So if I have X is an F distribution, its inverse, well, I just switch the degrees of freedom. Now, why do we care about this? Okay, so let's say it's back in the day when people had to use tables to look up probability values. Well, if I'm working with tables, not every single possible value can get printed out. It's just not feasible. There's, we only have like so much paper, and the books would get so big that they didn't want to print everything out. So what they would do is they would only print out the F distribution for, let's say, when D1 is less than or equal to D2. Well, if that inequality got flipped because of the situation I was in, what I would do is I would just take the reciprocal, and boom, we'd get it. Easy peasy lemon squeezy. Now, the next one, this has a connection to ANOVA and has a connection to the t distribution, specifically when we have 1 degree of freedom for the first parameter. All right, so when we have 1 degree of freedom for the first parameter, if x is, so let me back up. If x is a t random variable with d2 degrees of freedom, then its square is F distribution with 1 degree of freedom on the first one. All right, so why is that important to us? Well, what this enables us to do, if I'm in a situation where I'm using F distribution with 1 degree of freedom, I could potentially go with a t distribution instead, or if I'm using a t distribution, I could use an F distribution instead. Why is this important? Because sometimes some audiences prefer ANOVA, some audiences prefer t-tests. When I've been working with some people, some clients, helping them on their dissertations, their advisors have preferred the ANOVA, they preferred the F-test over the t-test, even though they're the same thing. So what we would do, we would just pick the one that their committee would be most ready to accept, because the goal is for the statistics to be accepted and believed. Now I want to go ahead and review some sampling distributions. So if y are independent normally distributed random variables with mean mu and variance sigma squared, then y bar sample average minus mu divided by sigma divided by square root of n, this is normal. This is normally distributed, and this should be a 1 there. I made a mistake there. And then here, if I have n minus 1 times sample variance divided by sigma squared, this is chi squared with n minus 1 degrees of freedom. And now here, this is the t distribution. If I take y bar minus mu, and instead of sigma, I put sample variance, or sample standard deviation divided by square root of n, then this is t distributed. All right, so now let's take a look at the F distribution in R. So if I have x and q are vector quantiles, P are our vector of probabilities, N is the number of observations, and df1, df2 are degrees of freedom, then we can get the density function using df. And here is what it looks like when I have 5 and 10 degrees of freedom. Here is my cumulative distribution function. Here's the quantile values for the box plot quantiles. Notice that it starts at 0 and goes to infinity. And here is the random number generation. Well, that's all I've got for you. Take care and goodbye.